I introduce Dr. Davies, let me give a number of people well-deserved thanks. I thank our College of Science ambassadors. Heather Hall is here. Owen is someplace busy handing out papers. I thank the Science Unwrapped committee who makes these events possible. And I thank all the people who have helped within the College of Science in getting things set up. And I especially thank our presenters who will have just a ton of really fun hands-on activities after the talk. And these people spend hours, all right, preparing their activities. We don't pay them, you can believe me on that, okay? And it's really great, okay, to reach out to the community with real hands-on science. So I really thank everybody who makes these events possible. My name's Greg Podgorski. I am the Associate Dean in the College of Science, and I am also chair of the Science Unwrapped Committee, something I really love doing. I told you a bit about Dr. Davies' talk and the title. Let me tell you a bit about Rob Davies. Rob is a physicist, and his work is focused on a number of different things, including climate change, and that's the theme of our Science Unwrapped for this year, changes of all things, but global change, complex systems, and human vibrancy. And you'll hear tonight how global change and human vibrancy are really very closely related. Rob is a native of South Dakota and grew up in the Black Hills. He's worked for NASA on the International Space Station. He's been part of the Utah State Space Dynamics Lab and the Utah Climate Center. Rob was an Air Force officer where he was also a meteorologist. He's currently professor of professional practice in the USU Physics Department. USU Ecology Center also gets Rob's help. And Rob is heavily involved in the Kane College of the Arts. And Rob asked me to put a little pitch in for something I think is really a wonderful activity that is the merger of science and the arts. And that's something Rob and his wife have been involved in for a long time. Rob's wife is a violinist in the Fry Street Quartet, and they have a special 10th anniversary performance of Rising Tide, which is part of their Crossroads project that brings together science and the arts. That will be November 14th in the Danes Concert Hall right here on campus. So I am going to get out of the way and turn things over to Rob for his talk of Fantasies of Continuous Growth, saying the quiet part out loud. Okay, thank you.
There we go. Okay, we'll switching. So we handed out some paper. It's kind of a fun activity. We're going to do. Did anybody not get a piece of paper who wants a piece of paper? You're going to need it right now. Okay, up here. So first of all, thank you all for coming out. It always amazes me that so many people come out on a Friday night to listen to a scientist talk about something. So thank you for that. So if you have your piece of paper, I just want you to look at it. Look at the edge and look at how thin it is. Just look at how thin that is. Now, I want you to take that piece of paper and fold it in half. And look at what you did. You just doubled the thickness by just that one fold. Now let's just stop there for a second. But imagine if you were to fold this just 8 more times, you would have a piece of paper about 1 inch thick. Go ahead and try it. See how many times you can fold your piece of paper in half. Keep folding it in half. Okay, show of hands. How many people got to 9 folds? Anybody get to 8 folds? Oh, we got one hand over here. Let me see it. Pretty good. Is it about an inch thick? Pretty close. Maybe if you got to 8 folds, it should be a half an inch thick. Okay. We'll stop folding the paper now. So maybe if the paper was a little bit bigger or you were just a little bit stronger, you could have folded that paper 9 times and got a piece of paper 1 inch thick. But now imagine if you could just fold it 4 more times. You would have a piece of paper 1 foot thick. Now that's 13 folds. And now imagine if somehow you could fold that paper less than 13 times more, just 12 times more. You will have a piece of paper 1 mile thick. I'm getting the sense some of you don't believe me. We're going to come back to this. So we're talking tonight about change. And that's good because I'm a physicist who studies change. I used to be a meteorologist, like Greg said, which was changes in the weather. But these days I study much bigger changes, bigger than the weather even, global changes. Changes all around the planet, changes to land, changes to forests, changes to oceans, to the atmosphere, changes to all the living bits on the planet, the biosphere, and changes to all of us people, too. The whole smack. And it turns out there's quite a lot of change going on. And some of this change is pretty good. I like to ski. And if I mess up my knee skiing, if I mess it up really bad, turns out they can give me a whole new knee. They couldn't do that when I was a kid, but they can now. So that's a pretty good change. When I started studying physics, let's see if I can pull this out here. I used to spend endless hours, days, weeks in the library looking information up. Now, I can do it at my lunch hour with this thing that seemingly has no moving parts. So that seems like a pretty good change. But it turns out there's also some other big changes going on that are not so good. In fact, they're pretty bad. Things like climate change. Things like much stronger and more destructive storms, floods, fires, rising seas that are disrupting tens of millions of people. My mother just went through a big hurricane in Florida. And disrupting more than just people, but whole nations. Some nations falling into war because of these changes. And disrupting and wiping out billions of living creatures. In your lifetimes, 1 million different kinds of creatures could go extinct. 1 million different kinds of creatures could go extinct in your lifetimes, and that would be absolutely terrible. In fact, catastrophic for us people, because we depend on those creatures. So that's the bad news. The good news is we understand this change is happening, and we understand why. Our science understands this change. The bad news is not nearly enough of us understand the science right now. Lots of us understand these changes are happening, but we don't understand that they're connected, like symptoms, like a sore throat or a fever, of an underlying illness. Now, the good news is our science does understand what this illness is. So some of us know, but not nearly enough of us know. And even those of us who know, sometimes we won't believe what we know. That's kind of interesting, isn't it? We'll come back to that too. So what I want to do tonight is tell a story. And the story I want to tell is a story of how things grow. And I'm talking about organisms, all the way up to animals, even people. But I don't want to stop at just how people grow. We're also going to talk about how things like whole cities can grow, and whole collections of cities and countries. In fact, the whole of human civilization can grow. And I want to tell this story because it turns out that growth is a very special and very powerful kind of change. And it also turns out that too much growth is the illness that's underlying all of these pretty terrible symptoms. And if I tell this story really well, then we're all going to know. And if I tell it really well, not only are we going to know what this illness is, we're going to believe what we know. And that's really important because the more of us who know, then we can help other people know. And that is by far the most important step right now in helping us change these pretty terrible changes. Okay, so you ready? Now the first thing, of course, is as good scientists, we really need to be sure what we're talking about. So I'm going to start with this word growth. And we use this word growth in all kinds of ways. And that's okay. That's perfectly fine. So for you guys, you kids, your parents probably tell you they want you to undergo some personal growth. They want you to grow mentally and intellectually. They might want you to grow spiritually. And what they mean by this is they want you to improve. They want you to get happier. They want you to prosper and flourish. They want you to flourish. They want you to progress. And all of that sounds pretty good. We're not talking about any of that. Today, when we talk about growth, we're only talking about getting bigger. That's it. Just getting bigger, not getting better, not getting more modern, not getting more developed or not flourishing, not getting happier, just getting bigger, period. Okay, so what do we want to know about growth? There's just two things we need to know, a couple of things, two pieces of things. One is the math of growth, and one is the physics of growth. So let's start with the math. Math of growth. Now, it turns out there's different ways things can grow, get bigger. So imagine you've got a box and you like to collect baseball cards. Does anybody in here collect baseball cards? Is that a thing anymore? I don't even know what we collect. Okay, we've got someone who collects baseball cards. You? Okay. You've got a box. You collect baseball cards. Here's your box, this whole screen, and there's your one baseball card that you have right there in the middle, that little black pixel. Now, one way you could grow your collection is you could add one baseball card, let's say every year, or maybe every month, or maybe every week. In fact, we want to grow it faster. Let's grow it every second. You're going to add one baseball card. There it is. And the next one, and the next one, every second. And if we keep doing this, if we keep adding baseball cards to your box is going to fill up in 10 and a half hours. If I just kept doing that. But it turns out there's another way to grow. Instead of adding a baseball card every second, let's double the number of baseball cards you have every second. And let's see how fast it takes to fill up our box then. So I'm going to take one of your cards, I'm going to stick it up there in the corner. Did you see that? And now we're going to double it and you're going to have 2, and then we're going to double it and you're going to have 4, and then we're going to double it and you're going to have 8. And let's see how long it takes. You ready? Go. Whoa. How long did it take? About 15 seconds. And this is a different kind of growth. That first kind of growth was called arithmetic growth. You don't have to remember that. This kind of growth is called exponential growth. And that's the kind of growth we want to talk about. And exponential growth is particularly powerful. And it's particularly sneaky. In fact, it's so sneaky, a very famous scientist once said the following: the greatest shortcoming of the human race is our inability to understand exponential growth. Okay, well that sounds pretty strong, so let's try to understand exponential growth. And let's go back to your folding the paper, which was exponential growth. We doubled it every single time, right? And so here's the equation, the math, that tells me that you're going to get a mile-thick piece of paper after 25 folds. Okay, you got that, right? I mean, that's pretty self-explanatory. I think you all understand that equation. No? Okay, well, let's try to understand this equation. It turns out it's not that hard. But before we try to understand this equation, let's just see what it looks like if I put it on a graph. So here's the number of folds as we go across the bottom, and here's the sneaky part about exponential growth. It seems like it's not doing anything for a long time. It's just small and small and small and small, and all of a sudden it goes from tiny to huge, just like that. A foot to a mile in just 13 folds or 12 folds, okay? So it's sneaky. It sneaks up on you. So let's understand that equation. How do we grow something exponentially? We start with a certain number of baseball cards, let's say, and then we grow it by some fraction. And then we end up with a new number, and then we do it again. So let's say we start with 1,000 baseball cards, and we're going to add every year 1/10 of how many I have. So 1/10 is 10%, right? So I'm going to grow at 10% every year. So what's 10% of 1,000? What's 1/10? Anybody? 100, right. So I'm going to add 100 this first year, and at the end of the year, I'm going to have 1,100. So I'm going to start the second year with that many. And what's 10% of 110? Sorry, of 1,100. I gave away the, didn't I? It's 110, that's right. And so now I've got 1,210, and I start the third year with 1,210. What's 10% of that? Exactly, 121. So now I add that in, and I start the fourth year with that number, and I end up with this number. But here's the thing. This is how it's different. We're not adding the same number of cards every time. We're adding the same fraction, but it's not the same number. It keeps getting bigger because the number we start with keeps getting bigger. Okay, good practice. Let's try one more, just so we got it. Start with 1,000 again, but now we're not going to grow. Our fraction of growth isn't going to be 1/10. It's going to be 1/2. What percent is that? 50%, exactly. Good. So now, what's 50% of 100? Right? So now I got 1,500, and that's where I start the second year. What's 50% of 1,500? 750. Good. Man, you guys are great. Okay, so we're just going to keep doing that for another few years here, like we did before. And once again, look at how much bigger every year the number that we add. So this is the power of exponential growth. And now we can understand our piece of paper. What did we do with the piece of paper? What was the fractional size that we grew every time? It was 1. We doubled it, 100% every single time. That's doubling. So now we can understand this equation. We started out with a piece of paper that was 2/1000 of an inch thick. We folded it once, that doubled it, so that's times 2, but then we did that 25 times. And that gave us a mile. If you could fold that piece of paper 25 times, it would in fact be a mile thick. So that's the math. And that's pretty much all we need to know about the math. So now let's do the physics. Okay, and we're going to go back to the folded paper one more time. Because this is where things get tangled up. This is why even really smart people can't quite believe what they know about growth. Because they get the physics and the math tangled up. The math tells us this is how thick the paper will be as we keep folding it. And there's no end. We can just keep folding it. There's nothing in the math that says you can only fold it so many times. That's in the physics. Because you know that there was something there that stopped you, right? And that's because the physics of the material world always supersedes the math of unlimited growth. The physics always supersedes the math. The math says this, but in fact the physics says this. In nature, systems don't grow forever. They grow to a maturity and level. You got that paper folded only so many times and then it leveled. Now, this is called, by the way, just in case you're interested, it's called logistic growth, but you don't have to remember that either. It's exponential sometimes at the front end, but that exponential growth can't last, then it starts to level off. We just saw this happen with the coronavirus. It grows fast at the beginning, but then there's a physical limit, and the limit is the number of people it can infect. And once it gets to the maximum, it levels off. And we know that this is how real creatures grow, right? I mean, a little bear cub can grow into a mature bear, but those mature bears don't keep growing to the size of a city. We don't have bears stomping around crushing cities, right? Because there's some physical limit that stops that organism from growing. And it has to do with their environment and their genes and all of that. So the question is understanding what that physical limit is. Now, it turns out there's another way things can grow. In nature, things can grow past their physical limit. We can grow things past their physical limit. Imagine you're running super fast, and we're growing how fast you're running. And you get to your maximum speed, but you just can't keep it up because it's not sustainable. You just can't keep it up, and you run so hard that finally, and this happens in nature, you crash. You overshot your physical limit, and you crashed. And we know that this happens. This happens with populations of creatures. that overgrow the ability of their environment to support them, like there's not enough food, and they can crash. Even human societies can do this. On a place called Easter Island in the Pacific, a group of people called the Nanapui crashed their population in the late 19th century. They lived on an island, and part of the reason they crashed was they overconsumed the resources. The island couldn't keep up. So we know that happens in nature too, but what doesn't happen in nature is the growth just continues forever. So there's a physical limit, and the question is, what is this physical limit? What determines that? And to answer that, we just need to ask, well, what do things need in order to grow? And if there's a limit on those things, maybe we can start to understand that. So how do things grow? Things use energy to take in stuff, and then if you do that, you have to put out some waste. We all know that, right? So this is how we grow. We use energy to take in food, and we get more energy from that food, but then we have to put out some waste. We have to go to the bathroom, right? But this is not only true for living creatures, this is also true for whole societies. Let's take a city. Let's take Logan. Logan uses energy. We used to bring in coal on trucks. And then we would burn that coal to bring in more stuff and to do stuff in our energy, and then we would put out waste. Go to the dump, we put out a lot of waste. And we call this process a metabolism. And a metabolism applies not just to living creatures, but also to whole cities, to whole civilization. There's a metabolism where we use energy, we take in stuff, and we put out waste. And everything does this. Now, I've used this word energy, and I want to spend a second on this word energy. This is another one of those words we use a lot, and we think we know what we're talking about. And we talk about solar energy and wind energy, and we talk about geothermal energy. I need enough energy to go to school. I eat breakfast to get some energy. But it might surprise you to know that even we physicists, at the end of the day, we kind of have to hem and haw when you ask us, what is energy? The physicist who answered this question the best is probably the most famous scientist in the whole world. Is this guy. Who's that? Einstein, right. Man, you guys are quick. And Einstein wrote down probably the most famous physics equation ever. There it is. E equals mc squared. And it's an equation about energy. There's the energy right there. And it's an equation also about stuff. There's the stuff right there. We call it mass. Right? It's anything you could touch. There's some mass right there. Wood, steel, even air is mass. Water is mass. You are mass. So it's just stuff. And c is the speed of light. We don't need to worry about that. And this equation is pretty cool. It says a lot of interesting things. But for us, the most interesting thing that it says is, secretly, energy is stuff. And stuff secretly is energy. Energy and stuff is kind of secretly the same stuff, turns out. So if you have stuff, you can get energy, and if you have energy, you can get stuff. And that's kind of what we need to know right now. So when I talk about what something needs to grow, energy and stuff, and then we put out waste, a place to put the waste, for our purposes tonight, we can just focus on the energy part. We don't need to talk about stuff because secretly it's the same. Now, we could talk about it, but you can sort of imagine, like we get to a place, kind of like in Star Trek, where they don't need stuff. They just walk up to the wall, and there's this machine there, and they say, give me a sandwich, cucumbers and hummus and some mustard and a pickle. And it just does it. It makes the stuff out of energy, right? Now, we are nowhere close to being able to do that, but you could sort of imagine with Einstein's equation, it might be possible sometime way in the future. So if we want to talk about what we need to grow, we can kind of, for the moment, forget about the stuff and just talk about energy. That's what I want to do. Okay. What's next? So what is energy? Well, Einstein answered it. Energy is kind of everything. But that doesn't really help us with our discussion. A better way to put it for us is to say that energy is the master resource. You can always substitute. When you want to do things, sometimes you can substitute one thing for another. You could build a house out of stones, or you could build a house out of wood. But what you always need is energy. It is the master resource. Okay, so that's what energy is. More interesting, though, actually, even for physicists, is not actually what energy is, but what does it do? And what energy does is it makes things move. And this is important because everything involves motion. Any activity you can think of involves motion. In fact, I challenge you to think of a single thing you could do that does not involve motion. I'll give $1 to anyone who can think of anything that does not involve motion. Give me some suggestions. What? Yeah. Dying. Oh, God, I got to think about that. Is that something you could do? I mean, in the process of dying, that last breath, your chest sinks. I think it moves. That's the closest I've ever seen anyone come, but I'm not going to give it. Back here. Imagining. Oh, I love that answer. One second. He said imagining. Just sitting there. Now, you're just saying you're sitting there still. You're not even breathing, right? You're just imagining. But there is something moving. Does anybody know what's moving? You're using your brain. Yeah. Oh, wait, I'm still on imagining. Okay. You're using your brain, and brains are electrical activity, and electrical activity involves moving electrical charges. Now, granted, they're very small, but they're still moving. And if they stop moving, you will stop imagining, I promise. Okay, so being in a coma, I'll take that last one. You're still breathing. Your metabolism is still happening inside your body. Lots of things are moving around inside your body. You're still alive. The death thing is pretty close. Okay, so everything we do, all activity involves motion. Now, if all activity is motion, and if energy is what makes things move, then doing anything means you've got to have energy. There's nothing you can do without energy, not a single thing. So that's what energy does. Where is energy? Okay, so we need energy to do stuff. Where do we get it? Energy is in two places. Energy is in moving things. We know this, right? So picture a bowling ball. We know there's energy in the moving bowling ball because what does energy do? It makes things move. And that moving bowling ball makes the bowling pins move. So there was energy inside that bowling ball, right? So energy is in moving things. And that's true for bowling balls, and it's also true for atoms and molecules. Energy is also in arrangements of things. This is a little bit, you got to think about this one for a second. So what do I mean by that? So imagine arranging three things: a person and a bow and an arrow. We know there's energy there because that arrangement can make it move. So that energy was stored in that configuration. And in fact, it's easier to see if we use atoms and molecules. Atoms join into molecules when they hook together, and they hook together with a kind of a spring. Think of it as a spring. It's not really a spring, but it's kind of like a spring. And when they hook together, there's energy stored in that bond. And when that bond breaks, they fly apart, and the energy goes into the motion of the atoms. And then they come back together, and they store it in the spring. And then they go apart, and it goes into the energy, and they come together. And then if it happens really fast, if they break apart super fast, we call that an explosion. And things go flying all over the place, and eventually maybe sometimes they recombine and store the energy there. So the configuration, this is where the energy is. In the configuration of things and in motion. Okay, fine, that's where energy is, and we need energy, so hopefully we can find it in moving things and in configurations. But just as an interesting question, could we make energy? And the answer is no. And that's a hard no. That's the law. And this isn't like a law that can change. Like maybe your parents made a law when you were 7 that you had to go to bed at 8 o'clock. But then when you were 10, you could go to bed at 9 o'clock. So you can change those laws. Or maybe the city council decided we need a stop sign at that intersection that we didn't have to stop at before. We changed the law. This is not one of those laws. This is an absolutely unchanged, this is law. This is a natural law. And it's such an important natural law, a prime natural law. We give it the most important name we can think of. We call it the first law. And the first law says that you can never make energy and you can never destroy energy, but you can move it between different forms. It can go from being stored in motion to being stored in configurations, but you can never, ever make energy. So let's see how that works with a car. You get in a car, you start the car, and there's energy in the gas. And when you start the car, what you're doing is you're breaking apart those gasoline molecules. So all that energy that was stored in the configuration, it moves the pistons. You moved it from the stored energy in the molecules to the motion of the pistons, and those pistons transfer that motion to the wheels, and those wheels grab the road and transfer that motion to the whole car. So we just transferred the energy from inside the gas molecules to the motion of the car. There it goes. Okay, now you say, oh, what happens when you slam on the brakes? Where'd the energy go? We said you can't create it, and you also said you can't destroy it, but we had all that energy of motion, and now it's gone. Anybody know where it went? Yeah. Heat from friction in the brakes, right? That's exactly right. So there's the brakes. And what is heat? Heat is just the motion of molecules. And the hotter the temperature, the faster they're moving. So all that energy went from the gasoline tank, finally ended up in the heat of the brakes. It's still there. It's in motion. And then it just gives the heat, the brakes cool off because they give the heat to the air around it. But the air heats up, so the environment heats up. So that is the first law. Okay, so we can't make energy, but apparently we can just keep changing it around from form to form. So can we use the same energy just over and over again? Just transfer it from the gasoline to the pistons to the wheels to the brakes, and then from the brakes back to the gasoline, and just keep doing that. So can we do that? And the answer is no. And it's another hard no. It's another law. And this law is as important as the first law, but the name first law was already taken. So we had to give it another name that was almost as good as the first law, because this is as important. What do you think we called it? Yeah, we called it the second law. There it is. So I probably don't need to say any more about that. Maybe I do. What that math says is that when energy shifts from one form to another, some of it leaks away. Some of it leaks away. It becomes waste heat. So let's go back to the car. When we burned the gasoline and we took the energy from the molecules and put it into the pistons, we couldn't take all of the energy from the molecules and put it into the pistons. Some of it leaked away. It heated up the pistons. And then when the pistons moved the wheels, not all of that energy went to the wheels. Some of it heated up the wheels. And when the wheels grabbed the road, not all of that energy went into moving the car. Some of it leaked into the road. And this happened not because we weren't clever enough to build a really great car. It happened because of this law. The universe will not allow us to use all of that energy and transfer it and use it to do something. It's the law. So this is a pretty important law, and we call it waste heat. It's not really waste, it's we can't use it. It gets harder and harder to use as it leaks away. And what this says is no clump of energy can be used with perfect efficiency. I can't take any clump of energy and use it to do something without some of it leaking away. Now, another way to say that is, energy starts out as maybe high-quality energy. And high-quality energy is concentrated, and it's ordered, and it's useful. So think about, for example, wind, which is a bunch of air moving in the same direction, a bunch of molecules. It's ordered. They're all moving in the same direction in a river of air, and we can turn some wind turbines and make some energy. We can do something useful with it. But the second law says that when we do that, that high-quality energy eventually decays into low-quality energy, the thermal motion of atoms. And it becomes harder and harder to use that energy to do anything else. So we could turn the wind turbines with a wind, but when the air is still, we can't turn them to do anything with it. But the air that's still has a lot of energy in it. The air in this room, the molecules are moving at an average speed of about 1,200 miles per hour. The molecules in the air in this room are moving at an average speed of about 1,200 miles per hour. There's enough energy in a beach ball full of air to lift 200 pounds, 6 feet. It's just that we don't know how to get that energy to do it. And it's not because we're not clever enough. It's because the universe won't let us. Eventually, all the energy we use turns into unuseful, highly disordered, low-quality energy. In other words, another way to put this is, everything falls apart. Everything falls apart. If we build a house, and we build it really well, eventually something falls off. I promise you, just ask your parents. And then we spend some energy and get some stuff, and we put it back together, and then something else falls off. And this happens with everything, with buildings, with roads, with machines, with bicycles, with shoes. Everything. So what this means is, in the metabolism of things, not only do we need energy to grow, even after you finish growing, you still need energy, you still have to eat, because our bodies are falling apart all the time. Our bodies have to rebuild all the skin in our body every 2 weeks. Just sitting here, in the last minute, everyone in this room lost about 35,000 skin cells. Ugh. All that dust in your house, most of it is dead skin. So everything falls apart, and even when things get to full growth, you still need an energy flow to keep them ordered, to keep them built up. Everything falls apart. So now we've learned some things about energy. Let's review. The physics of growth is this: energy is the master resource. You can't do anything without energy. Energy can't be used perfectly, efficiently. Some of it always leaks away. It always decays from high-quality ordered energy to low-quality disordered energy. In other words, that means that everything falls apart. And you need energy to keep it together. So that's the physics of growth and the math of growth. So we're almost done. And now we just need a few minutes to put it all together. So I said at the start of all this that there's lots of changes going on, big changes, and some of them are pretty bad, and that needs to stop. And that was the bad news. But I also said the good news was we know about the changes, and we know how to stop it. And I said that the key to understanding that was understanding the physics and the math of growth, but I didn't say the growth of what. So what growth of what do we have to understand? Like maybe the growth of pollution, or the growth of conflict and wars, or the growth of us, people, the number of people. And all of that's important, but it's all just pieces of the puzzle. The underlying growth that we need to understand, and this is going to blow your socks off. You ready? Our collective civilizational activity. Doesn't it just roll off the tongue? Everything that we do as a civilization, we call this our collective civilizational metabolism. But other people, really smart people, call it the economy. All the stuff we do, collectively, that we do. And so we need to understand the growth of this collective civilizational activity, this civilizational metabolism, this economy. So we need to understand economic growth. And here's the challenge. Economic growth is what is the illness that underlies all of these pretty terrible symptoms. Oh, good job. Economic growth is the symptom that underlies all of these pretty terrible symptoms. But here's the complicated part. As a society, we have decided that economic growth is how we're going to solve all these problems. We have decided that we're going to solve climate change, we're going to make everybody happier, we're going to make sure nobody is homeless or starving or sick. We're going to fix all of this stuff, and the only plan we have to do it, the underlying plan, prime to everything else, is economic growth. We have to do that. Very smart people tell us that we have to do this. Lots of us. Okay, well, maybe that's not so bad. How much growth? Like, do we have to double the economy every year or triple it or something? No. 3% per year. Oh, it seems trivial. Just 3%, not like doubling it. There's a catch, we have to do that forever. And remember, the physics of a material world supersedes the mathematics of infinite growth. Everything stops growing. Remember that? Everything stops growing. So from the standpoint of these really terrible big changes that are happening, this is good news. This growth that's causing all of these problems or driving it or underlying it, that growth is going away. That seems like good news. Here's the bad news. If that growth goes away in an uncontrolled way, that we just crash, boom, overshoot to collapse, that is terrible for everybody. We don't want that. That is really terrible for everybody and everything. But here's the good news. We understand that this is happening, and we actually know how to do this. We've already, actually, as a society, overshot our physical limit. I haven't talked about stuff, I just talked about energy, but from the standpoint of stuff, we already use more than we can keep up using. But what we can do, and lots of physical systems do this, is we can come down. It's like if you did your sprint and you got to that top bit, but instead of keeping going until you collapsed, you just slowed down a little bit, below the physical limit. Caught your breath, kept running, then you could sprint a little more and go back up. It's called the dynamic equilibrium, and we can do this. We know how. So why do smart people think that we can just keep growing forever? Why do we think that? Two reasons. We're almost done. First is growth is sneaky, like we said before. It can fool us. It really can fool us. Remember our baseball cards? Yeah, back here. And remember how when we grew it at 100% per second, it filled up the screen in about 15 seconds. Now, instead of that being a baseball card box, let's say that that whole screen is all the stuff that's available for us to use in our civilization. It's the whole planet. And we're not going to grow the baseball cards 100% per second. We're just going to grow how quickly we use that stuff 3% per year. And if you grow anything at 3% per year, it will double in 23 years. It will double in 23 years. And in that case, it would take us about 300 years to fill up that first half of this, to use up that first half of the planet. And this is why it's sneaky, because for 300 years we've been doing this. And we're sitting here 300 years later and we're saying, man, we've been doing this for 300 years and we have still got half the planet left. Let's grow at 3%. At 3% growth, which has a doubling time of 23 years, we've used up half the planet in 300 years. How much time to use up the other half? 23 more years. That's how sneaky it is. We don't have 300 more years. You just got a couple of decades. Now, this doesn't worry lots of smart people. They say it's okay. The Stone Age didn't end because we ran out of stones. We can find substitutes, right? We can substitute wood for stones and concrete for wood, and we can substitute crude oil for whale oil, and then we can substitute solar panels and geothermal and wind for crude oil, and we can do all of that. Now, we've already talked about there's a limit to the substitution. We'll come back to that, but we still live on just this one planet. And we've used up now one planet's worth of resources, but let's do the impossible. Let's just grant the really smart people their wish, and through innovation, we will find 3 more planets worth of resources. Now, there's no reason to think we can do this. We are not going to do this. But let's just do a mental exercise and say we did. We did the impossible. Unicorns and fairy dust. Here it is. 3% growth. We've used up one planet in a little more than 300 years. How much time to use up the next planet? Yeah. No. See, it's sneaky. I understand. Doubling time? No. 23 years. 3% growth, doubles every 23 years. Now we've used up 2 planets, doubling time of 23 years. How much time to use up the next 2 planets? 23 years. So we did the absolute fantastically impossible and found 3 more planets, and it only bought us a few decades. Growth is sneaky. The other reason that really smart people just have a hard time believing what they know, that growth in the material world can't continue forever, is they forget that energy is a master resource. Yes, we can find substitutes for material stuff. Wood for stone, and concrete for wood, and carbon fiber for concrete, and we can just keep going on like that. But we can never find a substitute for energy, not ever. It's the law. We always need energy. And so, just a couple of more calculations and we're done. 3% growth, we can pretend that we get all the stuff that we need just from energy. We walk up to the replicator in the wall and tell it we want a sandwich, and it makes it for us out of energy. Here's what it looks like. So here we are today, over here on the left. Today, our human metabolism, our human economy uses 1/100,000th of the energy that reaches the Earth from the sun. There's a lot more. Now, the equivalent of that, we don't use all that energy from the sun. We use the equivalent of 1/100,000th that comes from the sun. But in about 300 years, if we're just doing energy, we would need all of the energy that reaches the Earth from the sun to run our economy. Now, that's not all of the energy from the sun. Here's the sun, here's the Earth. It's just that little bit of energy between those 2 lines that reaches the Earth. If we continue at 3% growth, in another 700 years, we're going to need the equivalent of all of the energy from the sun to run our economy. And if we continue another 800 years after that, which is only about 1,800 years from now, we would need all of the equivalent of all of the energy from the galaxy. That does not seem very likely. Now, you're going to say, hang on. That's 1,800 years from now. Surely we're going to have some technology 1,800 years from now that can produce all the energy we want. In fact, we're going to have right. Well, that's how you should feel. But in fact, we're going to have fusion. Fusion is this sort of miracle source of energy where you take just hydrogen out of seawater and it's perfectly clean, there's no waste, and you get all the energy you want. So what about fusion? We can't do it just yet, but some pretty smart people tell us we're close. The joke in physics is that fusion is 5 years away and always will be. But let's say that we finally get there. There's enough hydrogen in the oceans, in the seawater, to provide us with 27 billion years worth of energy. I mean, the Earth is only 5 billion years old. The universe is 13 billion years old. In another 5 billion years, the sun is going to blow up and destroy the Earth anyway. So it would seem like fusion gives us plenty of energy to take us through to the end of planet Earth. 27 billion years. There's a catch at our current level of consumption. But at 3% growth, that 27 billion years worth of energy turns into 850 years. And by the way, that's about as much energy as the sun puts out in a day. So it's nowhere close to the energy coming out of the whole galaxy. So fusion is not going to save us. And if you're still not convinced, remember, suppose we did get to using all that energy and somehow producing it here on Earth. Remember, all the energy we use eventually ends up as waste heat. It warms up the environment. Now, I'm not talking about global warming. That's different. That's the greenhouse effect from carbon dioxide in the atmosphere warming us up. This is completely different. This is just all the brakes in the cars warming up the planet and all of our machines. So if we start using all this energy, there's more and more waste heat. Now, right now, the waste heat from our civilization warms up the Earth just a tiny fraction of 1 degree. Can't even measure it. But there's an equation that lets us calculate what the temperature of the Earth will be depending on how much energy we're using. And when we do that calculation, here's what we find. We're on the home stretch. So fusion is out, but magically, because the very smart people tell us we're so smart and we can innovate our way through anything, we found some source of energy that produces all of it, but it's going to warm up the planet. It's the law. There is no way around this. In just 260 years, at 3% growth, the energy we use will warm the planet by 2 degrees Celsius. Now, this is the amount of warming that the climate change scientists tell us from global warming is dangerous. Very dangerous to humans, to human civilization. But this isn't global warming. This is the waste heat from all the energy we're using at 3% growth. And then just 25 years after that, we're going to be warmed up to 4 degrees Celsius. 4 more degrees Celsius, which is about 8 degrees, by the way, Fahrenheit. A temperature change in Fahrenheit is double the temperature change in Celsius, about. And then just 32 years after that, we will have warmed ourselves up 10 degrees Celsius, warmer than the planet's been in tens of millions of years. Just 83 years after that, we'll have warmed up 85 degrees, bringing the total planetary temperature to about 100 degrees. All the water will boil. And just 392 years after that, we'll have warmed up the temperature of the planet to the same as the sun. Do we have to worry about this happening? No, because civilization ends right about there. So we looked at the physics of growth, and we looked at the math of growth. We told a story, and the end of the story is this: growth will end. And it's going to end soon. End of story. Thanks for your attention.
Okay, for those of you who are staying for questions, it'd probably be helpful if you don't mind moving down. You don't have to, but it makes a shorter toss for this catchbox mic if people are sitting down here. So I think we're ready to start for questions. Questions? You got a question. What I'm going to do is throw this mic up. Ready? Are you a good catch?
So what I didn't kind of understand was that growth is actually gonna die and we're all like gonna die.
You need to speak up just a little bit.
That we're all gonna die in 300 years because of growth.
That what's going to happen?
Because we're gonna die.
How many years?
So the question is, are we all going to die in 10 years because of growth? Now, they only gave me 40 minutes. But the good news is, we know that this is coming. And even if we're a little slow out of the gate, we have more than 10 years. Okay? So no, we're not going to all die in 10 years because of growth. But we don't know exactly where the line is till things get really bad. So we're not sure when things start to get really bad. So the best thing to do, if you're not sure where the cliff is to stop well before you get to it, right? So the idea is we know what to do, we just need to get ourselves to do it. And part of doing that is helping people who don't understand that this is coming, that this is coming. Does that help? Okay. This young lady over here had a question too.
What do you think will happen when growth ends?
Well, it depends on how growth ends. If we let it collapse, it's not very fun, right? I mean, you remember what it was like when we shut down everything with COVID? Kind of like that, but a lot worse. But if growth ends because we plan how it ends, we know how to do an economy where we're all happy, we actually get better, without the need for economic growth. It's called a steady state economy, and we know how to do it. If we do it that way, not only do things not get worse, but they get a lot better. And the good news is, we know how to do it. So it's just about getting ourselves to do it, okay? Yeah.
Okay, other questions?
So what are kind of the practical ways we'll get down to that zero growth?
So what I didn't tell you, I think I lost this. Can I come back up here? I'm just going to show you one quick picture here. What I didn't tell you was, I kind of told you, but I didn't show you. Oops, not working. Well, what I didn't tell you is we're already over-consuming how much resources we need by about 170%. In other words, just to keep going like we are, we need 1.7 planets worth of resources. So we're already overshooting our limits, so we have to degrow to a steady state. So what are some, I'll just give you a couple of differences between a growth-based economy and a steady state economy. In a growth-based economy, what we do with efficiency, so we get more efficient at producing widgets, right? Let's say you work at a factory and you produce cars. And because of efficiency, because of machines, because we get better at it, the designs get better, after a while it only takes us half as much time to produce the same number of cars. In a growth-based economy, what do we do at that time? We make more cars. Exactly. And then we create a demand for those cars. We make the cars so they don't last. We do this on purpose. It's called planned obsolescence. So that, because what's the point? What is the factory trying to do? Is the factory trying to make good cars? The factory's trying to make money. And they have to because it's a growth-based economy. So if you shift to a steady state economy, we turn that efficiency not into more stuff, we turn it into time for the people who make the cars. So that's one example of how things are different, okay? And there's a whole sort of list of things that are different. It's a field of study called steady state economics, and you can look it up, and there's tons of videos and tons of people who tell you how a steady state economy works, okay? And in fact, right now, we don't actually have economic growth. I said we're growing, and we are, but it's not economic growth, it's uneconomic growth. Because now, the notion of economic growth is you get wealthier. But now, because we're destroying so much of our life support system, every bit of growth doesn't make us wealthier, it makes us worse off. We just don't always feel it right away, right? So not only, it's not a question of giving up things, it's actually a question of making things a lot better if you do it right. And the good news is we actually have a roadmap for doing that.
Other questions? Okay, guys, good catch. Let's see how good a talk.
So the calculations you have there, are those just for the human energy economy, so to speak? It doesn't incorporate any of the natural processes that are going on?
Good question. So we get energy from the sun, but we actually don't use, we use almost no energy from the sun. What uses the energy from the sun?
Plants.
All the living systems on the planet, right? And so, yes, the calculation I did, so we assume that energy coming in from the sun to do that calculation stays the same. And that we're generating our energy from some other source, like let's say fusion. And we already do that. Much of the energy we generate from burning fossil fuels. That's energy that came from the sun, but a long time ago. And it's stored in the configuration of the molecules, right? So the energy coming in from the sun raises us to a certain temperature. But then combusting all those, releasing that energy from the molecules raises our temperature more. That's what the calculation was. Does that make sense? Okay. So it did not include, the sun was the background, and then we added on top of that. Yeah. Oh, yeah.
So I believe that the birth rate in the United States was the lowest it's been in quite a while. Is that correct?
The question is the birth rate is below what?
Is lower than it has been in quite some time.
I think that's
correct?
right.
So do you think that it could possibly be that the economy could be used as a way to taper off growth?
So can the economy be used to taper off growth? And the way you phrase the question is what you mean by tapering off growth is tapering off population.
Yes.
Population is certainly a key piece of the equation.
Mm-hmm.
But right at the moment, it's not the most important piece of the equation.
Okay.
If we start pointing the fingers at population growth, we point the fingers in all the wrong places. The places on the planet with the highest population growth have the lowest consumption.
I see.
And so right now, our problem is not the developing world, the poor countries with higher population growth, but almost no consumption. 13 Bangladeshis to equal the same amount of consumption as a single American.
Okay.
The problem right now, the most immediate problem is consumption in these high consumption economies. Now, eventually down the road, yes, the population has to level, but that happens pretty naturally. In fact, it's already leveling globally. And the single best way to stop very large population growth, does anybody know? Say it again. Education of who? Women and girls. The education of women and girls is the single easiest way to bring population growth down to a sort of a manageable level and eventually level off. Right now, the projections for world population, we're at almost 8 billion now, and we're starting to level globally. And the projections show leveling after the middle of the century somewhere between 9 and 11 billion. Of course, that doesn't include the real problems that we're facing. Right.
So then, sorry.
Yeah, go ahead.
So then essentially when you're saying consumption, you don't necessarily mean just in food terms. I know there's a lot of food waste in the United States, but we're talking about like energy being put elsewhere that's not necessary.
Yeah, embedded consumption in all the stuff that we consume.
Okay.
Right. Consumption of all the stuff. Right? And this phone, and I try to make these things last as long as, my last one lasted 6 years. But the way our economy works is we're pressured constantly to consume more. We're told. And the beauty of this is what I love about this. This is not partisan. The one single thing in our entire country that unites the left and the right is economic growth. Doesn't matter what your political persuasion is, as a politician, you want economic growth. So, and that's about, a growth-based economy has to grow in order to thrive. If it stops growing, a steady state economy is not a growth-based economy that just stopped growing. That we call recession or depression, right? You have to structure the whole society, which includes public policy, for a steady state economy.
Yeah, which would require reform of our current government.
What's that?
It would require reform of our current government standards.
Yes, we have to reform basically every piece of our society. But again, the good news is we have roadmaps for that. Right? We sort of know how to do it. We just can't get ourselves to believe what we know.
Thank you very much.
Yeah. Up here, Greg. Okay, go ahead.
I'm just trying to understand the concept of why. So, if we were to try to tamper growth,
Economic growth.
does it have to do with how you said explaining metabolism? Like we use energy, we take in stuff. So, if I'm understanding, is it a way of better efficiently producing waste? Is that some way to kind of tamper?
It's a
Is it the use of waste or the transfer of energy through that helps tamper the growth? Am I understanding what you're saying?
So in the framework of metabolism, we're just taking in way more stuff and energy than we need. And in fact, you know, there's lots of analogies to this, but I just went through this a while ago. I injured my back and I had to stop exercising, and I just was eating more than I, was burning up. And I was getting bigger, and it was making me unhealthy. For me, that was making me unhealthy. You can consume any metabolism can consume stuff in a way that makes it unhealthy, not healthy. And that's what we're doing right now. So we just need to ramp down the amount of stuff. For one thing is, if we stopped incentivizing profit, then Apple isn't incentivized to make me want a new one of these things or need a new one of these things in another 2 years. Things last longer. But you have to have a whole society and public policy structured around that to get rid of the incentives where, I'll give one more example, our food system. is not designed to produce healthy food. It's designed to produce profit. So it's not agriculture for human well-being, it's agribusiness for shareholder return. And it comes with, we know our food system is unhealthy in many, many ways. So it comes with these costs. If we structure the public policy to get rid of the incentives and the society that requires us to want more wealth, there's sorry, this is wording on, I think I can summarize in the following way. George Monbiot, who's an environmental reporter and journalist, has been for many, many years, coined the following bumper sticker. What we want is personal and private sufficiency and public luxury. One of the reasons that we're all incentivized to try to get higher paying jobs, to make more money, to sell more Coca-Cola to kids or iPhones to people like me, is because we want security. We want security for our children, for our parents, elder care, child care, education, health care. We want all that. But in our society, the single largest cause for personal bankruptcy is our medical bills. That's not true in every society in the world. So if you have public policy that gives you public luxury, really good health care, really good education, really good child care, really good elder care, things like that, then I don't feel the need to accumulate personal wealth. I feel the need to accumulate enough to be happy. And in fact, the data shows since the 1940s in the United States, the amount of stuff that each one of us consumes has more than doubled. Just our personal resource footprint, right? How much stuff, a single person. But at the same time, our self-assessed happiness has gone down. So all this excess consumption isn't making us happier. And if we do it right, dropping the consumption, so how would I change my personal metabolism, my personal resource metabolism? I don't need an iPhone every 2 years. I need one every 10 years or 20 years. Something like that. That reduces my personal consumption a lot, right there. But that only happens in a society that's kind of structured to encourage that. And right now our society is very different. It's structured to encourage exactly the opposite. Yeah.
I'm going to toss this up and make this the last public question, and I think Rob will say for questions if people want to come down, just in the interest of everybody in the audience.
I was just wondering what models exist that you're of the steady state economy, or where do they actually do that?
Oh, well, I mean, these are economists. They call themselves, so sort of the mainstream economics is called neoclassical economics. And that's growth-based economics. And that's kind of what we've had for basically the last several hundred years, right? But mostly, well, neoclassical, really just the last century. The economists who do, and in classical, neoclassical economics, there is no environment. It's a linear production.
Yeah, and all the externalities are not taken into account.
In steady state economics, which is kind of a subset of something called ecological economics, we understand that the economy exists within the biosphere, the planet, right? And so you model these things with, this gets very technical, but it has to do with change functions and production functions and all of these sorts of things that economists deal with. But in ecological economics, they take into account that you have a finite resource base. That is not taken into account at all in neoclassical economics. In neoclassical economics, they brush all of this aside. Believe me, I've had so many conversations with mainstream economists, and they just look at me like, the problem is, Rob, you don't understand economics. You don't understand human. We always find a substitute. They brush all this aside with the word innovation. We will always find a way around these things, right? But hopefully, as we understood here, so now ecological economics doesn't do that. They include in the models that there is a finite limit of resource. And the real problem isn't that I haven't studied economics, mainstream economics. I don't need to study astrology to understand the main points of where it falls down because of physics. Sorry, go ahead.
Well, I'm just like, is there a society that?
Oh, yes, absolutely. So
Is there a like, what are we?
if you Google any of the following things, steady state economics, ecological economics, or degrowth economics, you'll find some wonderful resources. And maybe, can we put these on the website? I don't know.
The answer is we will look into it, Rob. I don't know.
Okay. So I'll give you some names right now if you can remember them. A great name, I'll give you 3 names. Kate Raworth, R-A-W-O-R-T-H. Oh shoot, I'm drawing a blank on my second name. The third name is a guy named Timothy Parrique, P-A-R-R-I-Q-U-E. And I can't remember my second name right now. I just drew a blank. Dan, I can't remember. Anyway, if you look up those 2 people, from there you'll find lots of resources on what a steady state economic system looks like and how it's different. And even some sort of policy prescriptions for how we start to get there. Yeah.
Thanks.
You bet. Thanks for coming, everybody.